Can you hear me?
Yep.
Okay. Oh, I gotta start the video, sorry. Hopefully this is better, we'll see. Anyway, we'll proceed and let's see what happens. Hopefully I get better. This is something I resorted to last semester. Let me just say something about the RLC lab, okay? Just as a reminder. Make sure you're gonna use a different marker. This one's dull too. Use the large multimeter to measure I sub m RMS, V sub r RMS. Oops. Let me just check something here. Okay, we're okay. V sub c RMS and V sub l RMS. The other meter that we had, a small meter, is not, the voltage scale on AC is bad. Okay, it only gives you voltages to 1/10 of a volt, so it's going to be useless for this experiment, unfortunately. The one I used over the summer was better than this, but we couldn't get it. So I designed the lab before we were able to get the equipment, and I apologize for that. So this is going to be kind of a pain in the butt to do, because it means that you have to take this meter, put it in the circuit, measure the current, take it out of the circuit, and then measure the voltage drops across these elements. Okay, I did send you a graph of the data I took over the summer. So a couple of things though regarding the graph. Number one, I used a signal generator that had a lower impedance, and there was evidence in the data. Okay. Yeah, all multimeters measure RMS values. Right. That's all you can get out of them is the RMS value. I sent an email. I actually sent 2 emails last night of the graphs I collected over the summer. The second one had, the more recent one had a couple corrections I added. So you should have gotten 2 emails. If you didn't get an email, let me know, because I sent it through Canvas. It's a Word document with just 3 pictures in them of the graphs that I plotted in SciMath. SciDavis, I'm sorry. Okay. Now, the second thing, use the 200 milliamp scale to measure IRMS. Okay. Just use that. The resistance on that scale is about 2 ohms. The document that I sent you in an email just gives you examples of what your graph should look like. That's a good question, Morgan. You should, right? I mean, if you don't, you'll really see the effect in this lab if you don't take the effect. Actually, in this lab, you're going to see the effect of the signal generator. When we do the lab on campus, the signal generator is a good one, and its output impedance is small. Ideally, it's supposed to be really small, but ours is not. That's why a lot of you folks had problems with the previous lab. So you'll actually see the effect of the impedance of the power supply. And in fact, the next thing I was going to say is, because you're going to be on this scale is about 2 ohms, the resistance, but a signal generator is of the order of 50 ohms. Yeah, and unfortunately, again, there's a thing, I got different equipment. When I did it over the summer, the signal generator, it looked exactly the same until you turned it on, and the writing was different, and in fact, the original one I had went bad. And that's why so now I have the same one you folks use. The original one went bad about a month ago. The one thing I worry is about the quality of this equipment. But anyway, the third thing I was going to write is the impedance of the signal generator is quite larger than the resistance of the ammeter. At least on this scale. If you use a 20 milliamp scale, the resistance is like 11 ohms. So that's like 20% of the signal generator, you would see the effect. But ideally what I wanted for this lab, I wanted the Q to be high, so you get a nice graph, but it's not going to be high, it's going to be low. But because it's going to be low, the peak will be wide, you'll actually get a nice curve fit. In fact, when you look at my graph, my data, the Q value was like 1 or something. Okay. When you do a similar lab in 215 with the driven damped harmonic oscillator, the Q is like 200. But with a Q of 1, you can really pin down the peak nicely. And you might not need to take as small steps as I had suggested. Okay. When you do it on campus, the peak is much narrower, and you have to almost go in 1 to 2 hertz increments. And that's going to depend on how good your meters are. This multimeter is pretty high resolution. Okay. So make sure you heed these. And yeah, this lab will be pretty long because you have to move the multimeter around. Okay. Like when we do it on campus, more internet problems. I will wait till we get a little bit of a connection here. Okay, we're back. That's good.
This meeting is being recorded.
Yeah, in the last class, it was constantly going out. I apologize. I don't know what the issue is today. What I was saying is when we do this on campus, the resistance of the meter is so low that our Q value is nice and high. It's not going to be so in this case. That's okay. You can still analyze the circuit, but then you can see the effect of other instrumentation in your circuit. You can see the effect of the signal generator. You can probably see the effect of the multimeter, and maybe some other stuff. Which is kind of nice that I chose a 1 ohm resistor in your circuit. Okay. So, any other questions on the RLC lab? Please let me know if you did not get the graphs of my data that I took over the summer. And my values, by the way, my values for L and C were different. Okay. So your graphs are going to be shifted.
So for the resistance of the multimeter at 200 milliamps, should we measure that and include that? Or should we just go with it's about 2 ohms?
I would go ahead and measure it because you're able to measure it. Right, because you have two multimeters.
So just measure it with the... measure with the other one yet.
Yeah, yeah.
Okay.
You have two multimeters. You can do that. In fact, I did this before class, so I mean, this is what I did. Can you see that? Can you see what I've done? I just connected one to the other. The little one's measuring resistance. The big one is set on current.
Mm-hmm.
And so you'll get a direct reading right away.
Right. And then for the total resistance of the circuit, we just add the 1 ohm resistor value to the multimeter value, right? Since they're going to be in series in the circuit.
Yeah, and you know what? You're going to see it when you plot Z as a function of omega. The graph kind of goes like this because it's kind of linear over here and goes with 1 over omega here. Right? It's kind of linear, right? Because it's not a parabola, it's going to be kind of linear. So the minimum is going to give you the total resistance of your circuit. So you'll see it there. Okay. So when you calculate this at resonance, use this value.
Okay.
Right? Because the graph will give it to you right away.
Because that's the impedance at the resonance frequency, right?
Yeah, and that's your
P.
total resistance of the circuit. Because
That's
X sub C cancels X sub L. So all you have is...
Okay, yeah, the resistance, yeah.
So it's going to give you your total resistance of the circuit. So you can put that in here. Because if you put 1 ohm in there, you're going to be way off.
Okay, so we don't necessarily need to calculate the R, we just get it from our graph?
Yeah, you can just get it from the graph. You can just say, I'm just going to get it from the graph.
Oh, okay.
Because you can say, and this, normally I don't talk about this, I let you guys discover this, but anyway, because students will come to me in open lab and say, hey, how come this is way off? And then I tell them, oh, that's because you have resistance in different parts of your circuit. But anyway, since we've talked about it, I mean, just use this value because this is a measurement of the resistance of your circuit, your total resistance of the circuit. Okay, and then when you do the curve fit, well, it doesn't look that nice, but when you do this curve fit, you can make R a fitting parameter and see what value of R you get. And that's what I did. I think on mine I got like 18.8 ohms in my circuit. Yours is going to be higher. This graph is going to be pretty wide in your case.
Okay.
Okay. But it's cool because you get to see all the effects in your circuit when you do this analysis. Okay. You get to see the effect of the signal generator, the multimeter, etc.
Okay.
And then you learn about how instrumentation affects your measurements. The only thing we're not looking at is the phase shift, unfortunately, but that's okay. Okay. So what I want to do is I want to finish off chapter 34, and then I'm just going to introduce relativity. I'm going to basically talk about the origin of thought. Where does everything come from? And then on Monday, I'm just going to talk about some of the repercussions. I can't talk about E equals mc squared, unfortunately. This is where you talk about this. I'm sorry?
Oh, I have one question.
Yeah.
It's not specific about the RLC lab, but are you going to give us a list of things that we have to return from the lab at the end of the semester?
Yeah, they're actually listed on each lab.
Oh, so we just look through each lab and look through which ones it says we have to return?
Yeah, and
Okay.
don't return the motor. That's yours to keep.
Yeah.
But
Okay.
the main things are the meters and the signal generator. I might have I think I have a list. I can email you the list.
Okay.
Okay. I think I might have a full list. I'll double check it, and then I can email the class. I also got to email you guys instructions. In fact, I'll probably do this before the end of the week. Tyler gave us some instructions about what to do. There's going to be a box outside of Sewell Hall for you to return stuff. So since you've asked, put your name on whatever container you put your equipment in. Okay, I need to know if you returned it, right?
Yeah.
So I need to see your name on the container. Yeah. Nice and bold. Just your name and the class. Actually, your name and the best thing would be your name and the CRN. Okay?
Got it. Okay, thank you.
All right. Okay, so let's talk about flow of energy. So one thing that the previous group noted was that when I was showing the PowerPoint slide, I was having less problems with the Zoom transmission as opposed to when I work on the board. But unfortunately, I have to work on the board on occasion. I will try to maximize the amount of time I have the screen like this so that the transmission's okay. So I'm going to look at the energy flow of electromagnetic wave through a thin box. And to make the math easy, I'm going to assume a plane wave, which means that over the entire surface of the box, the electric and magnetic field have the same value at the same instant in time. The electromagnetic wave is passing perpendicularly through that surface area. The volume of that box is the surface area A times dx. And we're going to assume that the energy is going perpendicular to the surface so that we don't have to worry about any tangential components. Okay? Because it's only the component of the electric and magnetic fields that travel perpendicularly through that surface that get through. If it's at an angle, then we have to worry about dot products, but we'll talk about that later. All right, so I want to look at the power per unit area, the energy per unit area, per unit time that's traversing that thin box. So the power is the time rate of change in energy. So that's my du dt. And let's assume the cross-sectional area of the green box is A. So I'm going to define S, our power per unit area, at any time as 1 over A times du over dt. But U is the energy density times the volume. Or if you have a small enough volume, dV, then du is the energy density times dV. Our element of volume is the cross-sectional area times the thickness of the box. My energy density consists of the energy density of the electric field plus the energy density of the magnetic field. And that's our total energy density. Okay.
This meeting is being recorded.
So du dt, let me go up at the, I have to go up to the board now. If du is U total times the area times the thickness of the box, then du dt Okay. But this is the speed of light. This term is the speed of light. Okay, so then S is u sub t times c, which is going to be equal to 1/2 epsilon naught e squared plus b squared over 2 u naught times c.
I hope this goes on YouTube.
This meeting is being recorded.
I apologize. I don't know what the issue is today. I guess I'm still having as many problems as before. And is the video you're seeing kind of choppy too?
No, the video looks fine. It's just
You freeze sometimes, but
I'm sorry?
other than that, you freeze sometimes, like stop moving, but it's not choppy. Like when you're actually moving, it's weird.
So like what I'm doing now looks weird?
No, it looks fine.
Okay.
Yeah.
It's just sometimes it stops moving for like a whole like 30 seconds.
Oh, that's... And it's weird. I don't know why it does that. I don't know what's causing that today. So anyway, I'll continue. If we reuse the relationship E over B is equal to C, then S, which is U sub T times C, and I got to be careful now. I really shouldn't put the M's here yet, okay, which I did in the slides. Can be written then, if I use this relationship in here, in other words, I can say E is B times C. If I put that into here, then what I get is B squared over 2 over mu naught times C. That's what S is. But I can also write it, because E is B times C, as E times B over mu naught.
Where did the E over B equals C come from?
Well, when I talked about earlier today, I showed you this slide. What was the equation? Yeah, I think it looked like that. I showed you a slide with an equation like this. And I said that this is perpendicular to these two.
Yeah.
Okay, so it came from that.
Okay.
Okay.
So if you have E over B equals C, but then at the beginning you said something about, in this example, E and B are planar, or use some word to describe it where E and B have equal magnitude, I think.
I didn't say they were equal.
Is that right or no? Did you not say something about that?
I didn't say E and B were equal magnitude. That's only true if C is 1. But I just said E over B is C. What I was saying is that in the equations, I have the maximum value in there. Right? I write E sub, if on the slide you see E sub M and B sub M. Yeah, I should really not put those in there because they're time dependent. I can write this as a function of time.
Right now, the C that we're using, that's the speed of light, right?
Correct.
Okay.
So I want to look at this expression. Okay. I'm going to look at that expression. If I want to, I can write the maximum value like that. Remember that the electric field and the magnetic field and the direction of travel of the wave, they're all perpendicular to each other. In fact, E cross B is in the direction of travel of the wave. So what if I took the cross product E cross B and divided by mu naught? What is that going to give me? Well, its magnitude is going to be E times B over mu naught. Because there's no sign of, the sign of theta is 1 because the angle between them is 90. And the direction of the thing is in the direction of travel of the wave. That's going to tell me the direction in which energy is flowing. So I'm going to define this vector called a pointing vector. Which describes the flow of energy of the wave. Okay? So this expression represents the flow of energy of the wave. So going back to the first two equations, we said that S was equal to 1 over A du over dt. Then S times A is equal to the rate at which energy is flowing through the surface. Okay, that represents the rate at which energy is flowing through the surface. Now, what if the electric field varies over the entire surface? What if the electric field varies over the entire surface? Then I can't do S times A. It turns out then I'd have to do the integral of S dA, and that's going to give you du dt. That's going to be the rate at which energy is flowing through the surface.
In what situation would that apply?
Suppose I have a spherical wave. If I'm very close to the source, the field is going to vary over that box. Because the spherical wave depends on 1 over r.
Okay, so you have the source
right next to the box.
A short distance from the box, so then the r increases as you move across the face, away from the point of, from the source.
The direction changes too, right? Over the direction of the field varies too.
Yeah.
Over the surface of the box. So that's so now that makes life a little bit more complicated. What if the field's doing this? Only the component of S perpendicular to this penetrates. The component tangent only goes along the surface, right? Mm-hmm. So I want the component perpendicular to the surface, and so then I have to do a dot product. And that'll give me how much energy is going through. You notice how often this thing comes up? That dot product with a vector?
Yeah.
Right, because we did it with the electric field, we did it with the magnetic field, etc.
Yeah, the perpendicular components.
Yeah, those are important, aren't they?
Yeah.
And you can do it with heat flow too. Okay, so this would be the more general term. Anyway, I'm just letting you know that. So, anyway, this S is called a pointing vector, and it represents how energy penetrates a surface, the rate at which energy penetrates a surface. So let me say a few more things about this. Typically, we look at the average, and from a practical point of view, we look at the average energy penetrating a surface. Let me make my slide bigger here. So I define the intensity as the average of the pointing vector. Let me rephrase that. The intensity is the average of the magnitude of the pointing vector. So let's say that's my pointing vector, and my electric and magnetic field varies sinusoidally with time. I'm assuming plane waves. I take the product of the two, then I end up taking an average of a cosine squared. What's the average of cosine squared? I get a half, right? So if I multiply these two together and average it over one cycle, then I just get E sub m times B sub m over 2 mu naught. And I is called the intensity. It's the average power per unit area, which has some practical importance. And I'll do an example in a little bit that shows you the importance of what this means. We can also write the average intensity as E squared over 2c mu naught. Again, using the equation E over B equals C. Or we can write it in terms of the magnetic field. So one of the things about this chapter is there's just a lot of equations. A lot of the problems are just plug and chug. We can also write the I average as U average times the speed of light. Okay, so now that we know a little bit about energy flow, we know a little bit about the properties of the waves, I want to do a fairly standard example involving electromagnetic waves. So let's say we have an electric field that's traveling in a negative x direction, frequency of 10 to the 8th hertz. The electric field, the magnitude is 50 volts per meter, and it's traveling perpendicular to the z direction. I'm going to know the expression for the electric field, the magnetic field, and look at the average pointing vector. So hopefully, I don't cut out during this example. So we're given frequency is 10 to the 8th hertz. And yes, I'm not being careful with sig figs, okay? E or E max, okay, 50 volts per meter. And wave travels in minus x direction. And it's perpendicular to the z direction. Let's start out by writing down some fundamental things. Let's find the wavelength and omega and k. So since c is f lambda, then lambda is equal to c over f. The speed of light is 3 times 10 to the 8th meters per second. And the frequency f is 10 to the 8th. So the wavelength is 3 meters. Omega is 2 pi f. Two pi is 6.28. And then K is 2 pi over lambda. 2 pi is 6.28, approximately. I'm not being careful with sig figs. So now we are in the position to write the expression for the electric field. So the electric field and I'm going to put a general direction. I'll just use E hat for the direction of the wave. This is an arbitrary unit vector, okay? We got to figure that one out. Now let's think about the direction of, let's figure out the direction of the electric field, the direction of the oscillation of the electric field. It's saying it's traveling in the minus x direction and it's perpendicular to the z direction. So which direction is it? Remember, the electric field, the magnetic field, and the direction of travel are perpendicular to each other. They form a right-handed coordinate system. So what must this unit vector be? Well, it's either plus j hat or minus j hat. It's actually, I left it kind of open. It's ambiguous based on the information I gave you. Let's assume it's in this direction. So there's really a couple. I'm sorry?
So when you say it's a right-handed coordinate system, is there a right-hand rule that we can use for it?
Yes.
Or
yes. This cross this gives you that.
So
all coordinate systems are right-handed.
So, but how do we know which one is which?
What do you mean?
Because depending on if you're using the right-hand rule and you use your pointer finger for one direction, your middle finger for the other direction, and your thumb for the third direction, depending on which direction you assign to each finger, you're going to end up with a different direction. So you can end up with either the positive j hat or the negative j hat.
Yeah, all I'm saying is I'm going to choose one of them.
You're just going to choose one of them. There's not a.
Then that's
there's
going to
not
have
a way of determining.
I'm sorry. I'm sorry. I interrupted you. Go ahead.
There's not a way of determining whether it is positive j hat or negative j hat.
No, unless I know the actual direction of the magnetic field.
Okay. So
I didn't specify enough information. That's all.
Okay. Okay.
So let's say I choose this, and I did this on purpose. Okay. Let's say I choose that. Okay. So then I know K, I know omega. What sign should I choose here? That's in the negative x direction, so I got to choose the plus value. So my electric field then, 50 volts per meter, cosine of 2.09 x minus 6.28 times 10 to the 8th t. J hat. What about the magnetic field?
1 second. So you chose the positive. You chose kx plus omega t.
Oh, yeah.
And why did you choose that?
Because the positive represents a wave traveling in the negative x direction.
Okay.
The negative represents a wave traveling in the positive x direction. I don't know if you remember, if you've done transformations from one coordinate system to the next in pre-calc. I mean, if you, and I'm really, I was trying to avoid this to save time, but if you try to write the wave in a reference frame that's moving with the wave, you'll see where that plus and minus comes from. You have a wave moving in the positive x direction. Okay.
So choosing plus for a negative x direction and choosing minus for a positive x direction is just like a definition, something that we're going to do all the time?
Well, it's not a definition. That's the way it is. In fact, when they talk about the Galilean transformation in about 20 minutes, you'll see where that comes from.
Okay.
All right? You'll see exactly where this comes from. Okay. So I'll go through that in a little bit more detail when I do the Galilean transformation. So you'll see where it comes from. So that's the electric field. The magnetic field, it should be easy because all I got to do is calculate this value, because we know that E over B is equal to C, so then B is E over C, which is going to be equal to 50 volts per meter over 3 times 10 to the 8th, which is about 1.67 times 10 to the minus 7. I'll write it down here. Should I put this for the direction?
Can you not just choose?
Well, remember that the direction of travel of the wave, E and B form a right-handed coordinate system, so that E cross B has to be equal to the direction of travel of the wave. So let me draw a coordinate system. Let's let this be X, Y, and Z. That's a right-handed coordinate system. And let me draw the direction of travel of the wave. Basically, it's going to be the direction of the pointing vector. Let me draw the direction of E that way. So if I choose the magnetic field to point upward, and I use the right-hand rule, put my fingers in the direction of E, curl them towards B, it's saying that the wave is traveling out of the plane of out of the page of the board towards us. It's saying the wave is traveling towards us instead of into the board. So this is wrong. Do you see that?
So it's E cross B, so...
E cross B has to be in the direction of travel of the wave.
Okay.
Okay. So then this has to be a minus. Now when you use the right-hand rule, you do E cross B. Your thumb points into the board, which is consistent with the direction of travel of the wave. If I chose this guy for my direction of the electric field, then this would have to be in the positive Z direction. Okay. This is the thing you have to remember, that E cross B is in the direction of travel of the wave.
So in this case, the B has to be in the negative K hat direction because we arbitrarily chose E to be in the positive J hat direction.
Yeah, because I didn't give you enough information as to which one is which one I should have.
Okay.
Okay. If I would have given you more information, then I would have chosen one of these ahead of time. But in order to be able to choose one of these, I'd have to tell you what the direction of this one was. Okay.
Okay.
Now, the pointing vector. Let's look at the pointing vector. The pointing vector is this times this divided by 2. So basically, I got to take this times this, take the average of it, and then divide by mu. So S average, I just want the average pointing vector, I don't want its magnitude, is going to be E cross B average over mu naught, which is going to be E max B max over 2 mu naught in the negative I hat direction, because that's the direction the wave is traveling. And so then I'm going to take E max, which is 50, times B max, which is 10 to the minus 7, over 2 times mu naught. I don't want to write it out. And this ends up being to minus 3.33 I hat watts per meter squared. That's the average pointing vector. Now, if I wanted the energy density, they wanted the average density, right? Then the average energy density is going to be B total squared over 2 mu naught, or B max squared over 2 mu naught. That's one way to write it, because remember, we have the equation. So we can write this actually 3 different ways. I forgot the 7 here somewhere. And when you work this through, I think you get 1.11 times 10 to the minus 8 joules per meter cubed. That's the energy density.
Your U sub T average is equal to, what is that in the numerator?
B sub m squared.
B sub m, okay.
Right, because UT is B squared over mu naught. When you average this, you're going to get a 2 out of it. Right, when you average this thing, it's going to give you a B max over 2 mu naught. Because again, you're going to be averaging a cosine. Where's the magnetic field? If you square this and take its average, this will give you 1/2. And then you'll have this guy squared. Yeah, this is average, if you can't see it.
And what are the final units for the U?
Joules per meter cubed.
Joules per meter.
It's energy density, energy per unit volume.
Okay, so should that be a lowercase u then? Instead of an uppercase?
Yeah, I thought it looks like does it look like an uppercase to you?
That looks like an uppercase U to me.
Okay.
It's not a problem. I'm just used to, the way that I do use. Oh, sorry. It's your the top one.
Oh,
top
okay.
left. That's a capital U to me because it doesn't have a tail. But
okay.
yeah. Okay.
I don't like using the letter U for symbols,
Yeah.
but that's what they use.
Yeah.
When you write it, it's
Okay.
tough.
I add tails and dots and crosses to my letters when I'm writing them down, but it does get difficult.
So I see you had a question regarding whether this is whether plus or minus is the definition or not. No, it's actually a physical thing. All right, it's actually a physical. There's a physical reason why plus means a wave traveling to the left and minus means a wave traveling to the right. There's actually physical reasoning behind it.
It's like shifting the graph, the whole graph.
I'm sorry?
I mean, is that like shifting the whole graph, like the wave travels? That means like.
Correct. It's like changing a graph.
Got you.
Yeah. That's why I'm saying if you took pre-calculus, you did a lot of that. So I remember my kids doing this in pre-calc, and they had to do these transformation problems. The same idea. Okay. So a couple more things I wanted to say, and I'm really running out of time. But anyway, how do we represent a wave? Let's start with a point source, and we're really close to a wave. And what do I mean by a point source? Something that oscillates sinusoidally with time that creates a disturbance, because a wave is really a disturbance. Just imagine I drop a pebble in the water. What happens to the water when you drop a pebble in the water? What do you see? All right, I drop a pebble in the water. Don't you see waves moving outward? Like this? Yes? No? Okay. So you see waves traveling outward. These are points of the same phase in the wave. These are called the wave fronts. Okay? So this is a spherical wavefront. So these are points in the same phase of the wave, like the peaks or whatever. And the separation between these is lambda. We're really close to the source, so we're assuming spherical waves. So we have a point source, so point sources produce spherical waves. Line sources produce cylindrical waves. We work with spherical waves and plane waves because the math is easy. We know that the total energy, capital U, is proportional to the maximum value of E or the maximum value of M, right? As the wave spreads out, each wavefront contains the same amount of energy. The energy per unit area here and let's look at the energy per unit time. Maybe we can look at the power per unit area. Okay, so if we want to look at du over dt, it's still going to be proportional to E sub m squared. Okay, let's look at the power per unit area. Well, if this is spherical, you get P over 4 pi r squared. That power is distributed over a bigger area, and bigger area as this thing travels outward. But the energy is the same. This guy is the same. So what must happen to the amplitude of the wave as you go further and further out?
Has to decrease.
It has to decrease, right? This has to go down. In fact, it has to go down as 1 over r squared. E squared has to go down as 1 over r squared. So so this amplitude has to go down as 1 over r. In reality, the amplitude goes down as 1 over r. If you plot the amplitude as a function of r, and it kind of goes like this. And when you are far away from the source, does this thing vary much?
No.
No, the amplitude is essentially constant.
Yeah.
When you're really far away from the source, what happens to the curvature of this sphere?
Less and less pronounced.
It becomes more like a plane, right?
Yeah, but
so when you're
term
far
is
away
for
from when you're far away from the source, this varies very little, and so then we say that the electric field has this form. I'll just put a generic unit vector. Okay. That's where this comes from. We're assuming we're far away from the source because the amplitude of field doesn't vary a lot. So this plane wave is an approximation to reality. But this is what we use so we can understand the physics. Does that make sense? In reality, the amplitude goes down as 1 over r for a spherical wave. For a cylindrical wave, it goes down as 1 over the square root of r.
So that formula for the electric field is an approximation.
Yeah, because really far away from the source, this curvature is almost straight. And so really, instead of having curved surfaces, when you're really far away, you say, oh, let's draw these. These are the wavefronts that are separated by lambda. So the wavefronts look like planes. And these are points of constant phase. Because this gets less curved as you get further and further away.
Is lambda a constant?
Yes. Lambda is a property of the source of the wave. So unless the frequency of the generator changes, then lambda will stay constant. So give you an analogy. Imagine if I have a string, okay, and I just wiggle it up and down. Mm-hmm. Okay. The rate at which I wiggle the string up and down is going to give me the wavelength. If I wiggle it faster, then the wavelength changes. The wavelength gets smaller.
Gotcha, thanks.
Okay. I mean, it has the same behavior, just that some of its properties are different from, me wiggling a string, because when I wiggle a string, each part of the medium interacts with each other. These kind of waves don't require any medium at all. Okay, so the next thing I want to say is, suppose I have a detector over here. I should use a different color. And laser power meters do that, what I'm saying right here. Suppose I have a detector of area A. I want to measure how much energy this is picking up. Well, it's not going to be measuring all the energy from the wave, but it's going to be sampling a portion of this surface area. So the energy this picks up is going to be the intensity times the area of the detector. This guy here is called the intensity. This is why the intensity is so important. Because the energy is distributed over a larger and larger area. So if you get further and further away from the source, and you have a detector, your detector is going to be observing less and less energy per unit time hitting it. The energy that the detector picks up goes as 1 over r squared. So if you double the distance, the energy is going to pick up as 1/4. That makes sense? Are we okay with that? Okay. Now, I want to add one last thing. And I'm not going to solve this problem. I'm going to look at it conceptually. And by the way, this idea you're going to see in Physics 215 when you talk about mechanical waves and optical waves. So I want to look at one more thing, pose one question. Let's go back to the capacitor and let's charge it. And I'm going to do a two-dimensional drawing. So here's a capacitor. I'm charging it up. The current's this way. So that means the electric field this way. This is plus, this is minus. Let's assume this is a long wire. So if the current's going down like this, then on this side of the board, over here, the field is out of the board. And using the right-hand rule here, the field's into the board. What I want to ask is, how was the energy flowing into the capacitor? Okay, I'm not going to calculate here the rate at which energy is flowing. I want to talk about how the energy is flowing. Which direction is the energy flow? That's the question. Well, to figure out the direction of the energy flow, I have to look at the Poynting vector. So, let me draw my right-handed coordinate system. My electric field points downward. So let's look over here, the direction of the energy flow. My electric field points downward. My magnetic field is into the board. Oh, I'm sorry, out of the board, sorry. My magnetic field's out of the board. So if we do E cross B is that way. So S points this way over here. Let's go to this side. Let's draw a coordinate system again. So the electric field's downward. And the magnetic field is into the board on this side. Let's use the right-hand rule. Put your fingers downward. That one's going to be tough to do. Let me get on this side. Downward, curling towards the magnetic field. Your thumb points that way. So S points that way. And in fact, if you go all the way around the capacitor, the energy is flowing radially inward towards the capacitor. So the energy flow is radially inward. Did you expect that? That's the energy, that's the direction in which energy flows. Okay. So I'm probably going to be going a little bit over, but I need to introduce the next chapter. So this is all I want to talk about in this chapter. Okay? The homework problems are basically manipulating the equations that I showed. Okay, and you know your problem on the exam will be a fairly standard problem.
Is the homework still due Friday?
Yeah, I cut it down to 8 problems.
Okay.
And they should go pretty quick.
Okay.
Okay, because a lot of them are just they're plugging numbers into an equation. They should go quick. Okay. And the reason why, because we need to do a relativity homework, and I'm gonna like cut that by a lot. Okay. So I'm gonna go through and find which problems to keep.
Because are we also going to be lecturing on relativity on Monday?
Yes.
Okay. And then the homework will be due before the exam?
Yes. I'm gonna cut it down to like 5 problems.
Okay.
It'll be short. And the relativity problems are not long.
Okay.
Okay. And the relativity problem generally it has to be a standard problem, especially given the time we've had to cover the material. Principle, it shouldn't be that hard an exam. For you guys, especially because I have less time than the other group, so you're probably only going to have 2 problems on the test. Okay. Cool. And this test is worth half of your other exams.
Yeah.
Okay, so it shouldn't be a hard exam. Okay, so what I want to do is talk about really the origins of thought and relativity. We're going to miss a lot, unfortunately, but it is what it is, I guess. Ideally, this is something, a topic that one would spend to do a decent job on it, maybe 2 or 3 weeks. But we're going to have maybe 1.5 lectures. Okay. And I tend to go through a lot of details and examples that maybe most people don't go through in a traditional class because they whip through the material. This is an interesting topic. So let me just talk about basically the origins of thought and the principles of relativity. So where did the idea of relativity come from? I mean, where did Einstein's idea come from? This is chapter 39. So consider a person standing still and a bus moving relative to that person. And there's things on the bus that are moving around. Okay. Now, how do I write, if I'm standing there in my reference frame that's not moving, notice that the stationary frame has no primes on it. The moving frame has primes on it. So let's say the bus is the moving frame denoted by the primes. The back of the bus is the origin. And the bus is moving to the right. The position of an object inside the bus relative to a person standing has to be equal to how far away the bus is at some time t plus the position in on the bus. So let me go on the board and draw this. So here's a stationary person. I have to draw longer legs. And here is the bus moving. And there's an object here a distance x prime from this origin. Okay, those should be x's, not y's. Okay, and the distance the bus is at some time t from the person is v times t. So the position of this object relative to this person is going to be x equals x prime plus vt. For this guy, x prime, for this guy, this guy is going to be notice the minus sign. So if I talk about a wave traveling in that direction, and I choose my origin up here, and this is a point in the wave, this is like a point on the bus, and I want to describe this point in terms of the other person's coordinate system, then I have to have a minus sign if this wave is traveling that way. That's where the minus sign comes in that equation. Okay.
Is the VT be given or it's
I'm sorry?
given, or that's we need to find out by ourselves?
I'm sorry, I didn't hear you.
The VT part, is that the given, or we need to find it by ourselves? Like how we got the VT?
How do we get the v times t?
Yeah.
Well, what I'm saying is that at some time t, the bus is this distance away. If the bus is going 30 meters per second, then after 3 seconds, it's 90 meters away, right? Mm-hmm. That's what this represents.
Got you.
This represents how far away the bus is at this time. Depends what t is, right? I just did it in general.
Got you. Thanks.
Okay. So if I want to know the velocity of this object, then what I got to do is take the time derivative. We're going to assume the bus is moving at a constant velocity. It's in an inertial frame. Well, if the bus is moving at a constant velocity, then this is just going to give me a v. This is the velocity in the reference frame that's moving. So the velocity that I measure is equal to the velocity relative to the reference frame plus the velocity of the bus. So let me give you an example. If I'm on the bus and I throw the ball forward at 10 meters per second, so if I throw the ball forward at 10 meters per second, and the bus is moving in the same direction at 10 meters per second, then you're going to measure that the object is moving at 20 meters per second. Doesn't that make sense? If I'm in a car, and you're just watching me, if I'm in a car, the car is going at 10 meters per second away from you, and I throw a ball at 10 meters per second relative to me, you're going to measure 20 meters per second. Okay? Now, if I differentiate these again, then if the bus is moving at a constant speed, this is 0. I'm going to get u du dt, which is an acceleration. I get that the accelerations are the same in both reference frames. So if I were on the bus and I dropped the ball so that it just fell to the ground of the bus, and a person on the bus measured the acceleration, and a person that's stationary measured the acceleration, they would get the same value. Because you're in a reference frame that's inertial. This is the Galilean transformation. Okay? And the Galilean transformation says that the net force on the system has the same value in all reference frames. Not only does Newton's second law have the same form, mathematical form, in all reference frames, but it has the same value in all reference frames. When something has the same value in all reference frames, that means it's invariant. So, for example, I'll tell you something that's invariant in all reference frames. If I measure the distance between these 2 points, let's do this. If I measure the distance between these 2 points on the bus, it's going to match the same distance. That person's going to get the same distance. The distance between the 2 points on the bus is going to be the same as if this person measured it. That's an invariant quantity. So distance is invariant, but position is not. Of course, the reason why they're going to get the same measurement is because each point here is moving at the same rate. Now, what about energy? What about conservation of energy and conservation of momentum? Does energy have the same value in all reference frames?
Not potential energy.
Not potential. And what about kinetic energy?
Right.
Kinetic energy and potential energy do not have the same value in all reference frames, but the equation for conservation of energy looks the same in any reference frame, right? So if I want to apply conservation of energy and I say, 1/2 mv initial squared plus mg y initial equals 1/2 mv final squared plus mg y final. No matter what reference frame you're in, this equation is going to have the same form. The only difference will be these numbers will be different. Isn't that true?
Yeah.
So the conservation laws, such that conservation of energy and conservation of momentum, they have the same form. They're called covariant. Okay? If they have the same form in all reference frames, they're covariant. In fact, all the laws of mechanics are covariant in all inertial frames. All of them. Okay, even Newton's second law.
So they have the same equation, just not the same values.
Correct. Right, because I can apply, because in physics 205, didn't you do conservation momentum problems in the center mass frame?
What was that?
In physics 205, in your first physics class, did you do conservation momentum problems in the center mass frame?
Maybe.
Maybe, okay, maybe
Probably.
You don't remember. But you applied conservation momentum in the center mass frame, and you also applied it in the lab frame. You got the same results. Mm-hmm. Okay, so that says that, okay. And basically you have, for conservation of momentum, m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. Initial momentum of the system before equals the final momentum afterwards. Okay, so no matter what reference frame you're in, this is going to be the form. It's just that the v's will be different.
And is that only in inertial reference frames or
yes.
in all reference frames?
But let's focus on inertial frames, because accelerated frames cause problems. That's where Einstein's general relativity comes in. We're not talking about that.
Okay.
I don't know that much about it anyway. The math gets nasty. Okay. Well, the principle of Newtonian relativity says that all inertial frames are equivalent in describing a mechanical system. The absolute motion cannot be detected. If you measure the period of a pendulum in two different inertial frames, you get the same results. How does the Galilean transformation work with Maxwell's equations? That's the question. This is what Einstein looked at. The idea of relativity, even though we apply relativity to mechanics problems, the idea of relativity came from the application of transformations to Maxwell's equations. If you apply the Galilean transformation of Maxwell's equations, you'll find that the form of the equations will completely change in a different reference frame. So something's wrong there. Why would that happen in E&M? What's so special about E&M?
So by saying they're in a different reference frame, is that saying that they're in a different reference frame from you?
Yes, like they're moving, for example.
Okay. So like, if we were to measure the electric field and magnetic field of a system in the lab, and then we were to take that and put it on an airplane, but we were to get onto the airplane as well, would the E&M or the electric field and magnetic fields change for us?
Well, you're in the plane with them?
If you're in the plane with them.
Well, then it's still the same reference frame then, right?
Okay, so it's still the same reference frame for you.
Yeah,
so like you're in the same reference frame, but if you're in a different reference frame from the system, then it'll change.
Yeah, you're comparing one person that's moving to one person that's not moving.
Okay.
Or one person that's moving with velocity v to another person that's moving with a different velocity.
Okay.
Okay. And you get different results. See, if you're moving together, then you're not moving relative to each other, right?
Yeah.
Okay.
Yeah.
So I'm going to give you an example. I'm going to give you an example that's a little bit different from the one I have in the notes here, because I just don't have time. Let me change this problem a little bit. Let me go to the board. Actually, no, let me not change it. I'm just going to do it the same way. Let's see. No, never mind. I'll change it. So, suppose I have two protons, because this will make it easier to see. They're both moving with velocity v in that direction. Okay, and I'm watching this. Okay, I'm doing the observation. They're separating by a distance d. So I'm changing the problem from the notes just because of time. So I'll try to be more conceptual. So these two guys are going to the right. And I want to know the force on the top proton. Okay? Obviously, there is Coulomb's law, which is not really, this is not really correct, but okay. Their separation isn't changing if they're both moving to the right though, right? So I can actually still use this, because even though they're both moving to the right, their separation isn't changing. But as I'm looking at it, if this guy moves to the right and I made a measurement here, I would actually measure a magnetic field. The magnetic field, due to the top charge, as a result of the fact that it's moving, because you have a moving charge. Moving charges create electromagnetic fields. You can actually use this equation to write down the magnetic field due to this guy I'm sorry, due to this guy at this point. So these charges are I'm going to say that they're both experiencing a magnetic field, one due to the other. Which means then that there's also going to be a magnetic force. So there's going to be an electric force plus a magnetic force. Because you know that the magnetic force is Q V cross B. So the upper charge experiences an electric force and it experiences a magnetic force. Because the bottom charge is moving, it creates a magnetic field. Just like a wire, right? If you had a bunch of charges along here moving in that direction, you'd have a current. So are we okay so far? So we can calculate the electric force and the magnetic force, okay? Let's not worry about what they are. Everyone okay so far? An agreement that this charge will experience both an electric force and a magnetic force?
I just have one question.
Yeah.
I think the problem says that the second proton moves parallel to the x-axis, but in the opposite direction.
Yes, and so what I said was I'm going to change the problem.
Oh, okay.
Yeah, so I changed the problem because in the interest of time.
Okay, sorry, I missed that.
All right. So, but you're okay though that you see that this charge is going to experience an electric force and a magnetic force.
Yeah, I see that.
Okay. Now, let me go in a reference frame. Let's go in the car. I'm driving my car at that speed. Okay? So I'm in my car going at the speed of these two protons. Imagine I have a super fast car that can go at the speed of those protons.
So now no magnetic field is being created.
Yeah.
Right?
Yeah.
So then the force on them would be different depending on your inertial frame?
Depending on your... So there's a problem there, right?
So then they would accelerate on different speeds depending on your inertial frame. How would that work?
Well, what that means is there's something wrong here.
Okay.
This is what it implies. There's something wrong here. Why should I get different values of forces? Okay, so this tells me right away there's a problem. So there's got to be some sort of way to correct it. Now, we're not going to correct the problem here, okay? We're not going to do, you don't do these problems until at least a junior level class. Okay, but we use this to introduce the fact that there's a problem. So what's possible here? Well, number one, here are the possibilities. It could be that Newton's relativity is not valid for electricity and magnetism. It could be possible that E and M is valid in a special reference frame. It is possible that Maxwell's theory is not correct, but the transformation is valid. The last possibility is that Maxwell's theory and the relativity principle is universal, but there's something wrong with the transformation. The transformation maybe is approximately correct. And Einstein chose to look at the latter. Einstein chose to look at the fact that Maxwell's theory and the relativity principle are universal. Why shouldn't the law of physics be universal? And he said maybe the Galilean transformation is not exactly correct. It's maybe approximately correct. Maybe it's valid at low speeds. By the way, that magnetic field effect that I talked about in that problem generally is kind of small. As long as the speed of the object is small compared to the speed of light, the magnetic force is really small, but still there. So Einstein chose the last item to look at. But there were people who thought of maybe that light travels in a special reference frame. And part of the reason for this was because the scientists at that time were very deterministic. And when this idea of electromagnetic waves came about, they said, there's got to be some sort of medium. Because when you learn about waves in Physics 215, waves travel because one part of the medium affects another part of the medium. Right? When I wiggle a string, the reason why there's waves formed on a string is because one part of the string exerts a force on the next part of the string. When sound travels through space, it's because the atoms collide with each other. But with light waves, that's not the case. And so a lot of the scientists didn't like that and said there's got to be some sort of reference frame for electricity and magnetism. And so they said the light waves require medium just like sound waves. And they call it the luminiferous ether. And there's a lot of research on this topic in the 1800s. And they said that the ether was very rigid because the speed of light is huge. And they said that the speed of light has to be measured with respect to this ether. And so the speed of light must depend on reference frame. So experiments were carried out on measuring the speed of light with respect to the ether. And guess what they found? They found they couldn't measure the speed of light relative to the ether. Michelson and Morley designed an experiment to measure the speed of light relative to the ether and got no results. Well, at the same time, Einstein was using, and I'm going to skip this for the interest of time. Einstein was saying, I think that the Galilean principle is approximately correct. And so what he said was, let's assume that all the laws of physics are the same in all inertial frames. That absolute motion cannot be detected. And we're talking about inertial frames, okay? And he extended the principle of Newtonian relativity to encompass all physical measurements, not just mechanics. So he was, you can see he was using the last choice, that all the laws of physics are the same in all inertial frames. Then he also said that the speed of light is the same in any reference frame. Now imagine, that the speed of light has the same value in all reference frame. So his postulates mean, though, and we're going to do this the first thing on Monday, postulates mean that time intervals are relative. You're going to have to change your frame of thinking now. This is a real effect, that time is different in different reference frames because of the fact that the speed of light is independent of the source. So on Monday, we're going to start with these two postulates and talk about their implications. And hopefully, we can at least talk about the Galilean, the Lorentz transformations. I never derive them because I never have time, but I state them. Even your book states them. But the Galilean transformations can be derived. In fact, the Lorentz transformations for relativity can be derived. You might say, well, why are they called the Lorentz transformations and not the Einstein transformations? And because Lorentz was trying to explain the results of the Michelson-Morley experiment, he actually came up with some of these expressions, independent of Einstein's theory. So that's why they're called the Lorentz transformations. So we'll see how far we get Monday. And I'm going to cut the homework down to maybe 5 problems on the last chapter. Okay? Thank you for staying over.
Yeah.
Thank you, Professor Calabrese.
Yeah.
All right. We'll see. If I don't see you in 210R, I'll see you on Monday.
All right. Thank you.
All right. You're welcome.